All right. You should have picking up the paper today, and we're going in order, so this should be the video. We're going in through the notes. You also have an It's Learning quiz that's due tonight. I'm going to do 2 example problems, 2 warm-up problems, and both of these should go on the sheet that you picked up today. This one has to do with energy, and the other one has to do with energy, and that's what your quiz is going to be about. Let's start with the first one. All right, number 1. So how do you know which equation to use? Should you use Q equals MCAT or negative MCAT equals MCAT? Well, all you need to do is look at the materials. So in this problem, they are only talking about one thing. They're only talking about a sample of metal. They don't mention anything else. They don't mention water. They don't mention copper. They don't mention anything else. So I know that this has to be the equation of Q equals MCAT. It tells me how many grams I have. That's a mass. They tell me the temperature difference. So I have 2 temperatures. I'll subtract them in a minute. They give me the energy, 159 joules of heat, which is energy. And they're asking for what is the specific heat capacity of this type of metal. So they're looking for the specific heat. You have to know what letter represents what. So if I'm looking for the specific heat, that is C in my problem, letter C. So I need to solve for letter C first. So I'm going to divide by m delta T, and I get Q divided by m delta T equals C. Okay, so there's my equation. I'm going to start with letter Q. Letter Q represents heat or energy. The only place I can see that is right here. It says 159 joules of heat was absorbed. So that's the number I will start with. 159 joules of heat. Okay? Divided by the mass. So mass right here, it's going to go at the bottom. So I need to get the mass at the bottom. In my problem, it says I have 20 grams. So I'm going to put 20 grams right here. 20 grams. Okay, great. Divided by delta T. So I'm going to put delta T also at the bottom right here. But I need to find delta T. I know delta T is equal to final temperature minus the initial temperature. And so when I'm plugging it in, I'm going to have the final temperature, which was 33 degrees in this problem, minus 15 degrees Celsius. And that's going to give me 18 degrees Celsius. That is my change in temperature, and that's what I'll put at the bottom. Here, I'll have 159 at the top, divided by 20, divided by 18. And I will get a specific heat in 2 seconds, 0.44 joules divided by grams degrees Celsius. None of my units canceled, so I had to keep all 3 units in there. Okay. That's the first one. That should be your number 1. That's what you put in number 1 for the warm-up. Number 2, here's your number 2. You should be writing it as well. So in this problem, if you read carefully, there are 2 things. There is copper and water. So since there are 2 separate things with 2 different masses, 2 different temperatures, I have to use negative MCAT is equal to MCAT. Okay? So since I know I'm using this equation, I need to label everything that I have. On one side is going to be either the copper or the water, and the other side is going to be the opposite, so either the copper or the water. So let's label. Let's start with copper. I need an M, C, and a delta T. And then for water, H2O, I need an M, a C, and a delta T. There we go. And so we'll just start reading the problem. It says I have 15 grams of copper. That is a mass right there, so let me put it in. 15 grams of copper. Is heated to 150 degrees Celsius. Remember, we always do temperature last. So let's skip the temperature for now. And dropped into a 30-gram sample of water. So that's going to be 30 grams of water. At an unknown temperature. If the final temperature after the mixture is 50 degrees, what is the initial temperature of the water? The specific heat of copper is, there's a specific heat, so 0.385 joules divided by gram degree Celsius. And that's it. That's all the information. Okay, so now we can do temperature. I am also missing a C for water, H2O. So remember, that's when you have to have memorized. The specific heat of water is 4.184 joules divided by grams degrees Celsius. All right, now I just need delta T for both. Remember, delta T is final minus the initial. So the final temperature in this problem is, the final temperature after the mixture is 50 degrees. So I'm going to put 50 degrees right here, 50 degrees, and 50 degrees. Final minus the initial. And so for copper, final minus its initial, copper was heated to 150 degrees Celsius. So minus 150 degrees Celsius. And that gives me negative 100 degrees Celsius. And that's going to be my delta T for copper. Whereas water, minus, it doesn't give me an initial temperature of water. That's what I'm looking for. So I'm going to put a TI there. TI. Okay. And so I know what I'm looking for now. I'm looking for that TI. So I need to plug in everything and then eventually solve. So let's do that. I need to know which side is going to be negative. It says the final temperature was 50 degrees and copper was at 150 degrees. That's what it started at. So that means that water has to be below 50 degrees. So since copper has such a high temperature, higher than the final temperature, it's going to go first. It's going to be on the negative side. So let me write it on the negative side. So we'll start with negative 15 grams. And then the specific heat, 0.385 joules divided by gram degrees Celsius. Change in temperature, negative 100. Is equal to, I have 30 grams. Then I have 4.184 joules divided by gram degrees Celsius. And I'm running out of room, so I'll write it down here. And then I'll have 50 minus TI. There we go. Close it. Okay, looking at my units. What units are the same on the left and the right? I have grams right here, grams right here. I have joules divided by gram degrees Celsius, joule divided by gram degrees Celsius. The only thing that's going to be left is degrees Celsius, so I need to make sure when I'm done with my calculations, my final unit is in degrees Celsius. Okay. When solving this, I can just combine all of this. I can multiply all those three together because they're all numbers. So I'm going to multiply all three of them together, and I'm going to get 577.5 is equal to. And then on this side, I'm going to combine these two because these two are just numbers as well. So 30 times 4.184. And so I'll get 125.52. And then I didn't do anything to the last part, which is 50 minus TI. Okay, so this is what I have so far. So I just combine the terms. Now I need to start solving for TI. So to get TI by itself, I need to divide both sides by 125.52. Okay. If I do that, on the left side, I'm going to get about 4.60. On the right side, I'm going to get 50 minus TI. And now, I just need to solve for TI. So, easiest way, I'm just going to subtract 50 on both sides. And so, I'll get a negative number here, so negative 45.4 is equal to negative TI. And to remove the negative, you can either multiply by -1 or divide by -1. It doesn't matter. Eventually, TI is going to equal 45.4 degrees Celsius. And so that is the initial temperature of water. Okay. So now, these are two example problems that are going to be just on your quiz, your It's Learning quiz. So make sure you get your It's Learning quiz done by Friday night. All right, in the notes, we're going to move on in the notes. So get your notes out, pause the video and get your notes out. We're going to phase diagrams. Remember, phase diagrams is the changes. So melting, freezing, vaporization, condensation, all those things. And so we learned this in the beginning of the year. This is a phase diagram. Okay. Here in each phase, in each section, I have a solid here, a liquid here, and a vapor or a gas. On my y-axis, I have pressure, and on my x-axis, I have temperature. Okay? So when I have a certain pressure and a certain temperature, my substance, my solid, will turn into a liquid, or it will turn into a gas, depending on the conditions. So let's just label a couple things. First thing, point A, right in the middle. Point A represents the triple point. The triple point was the point at which all three phases coexist. So I have a solid, I have a liquid, and I have a gas all at the same time. Point B, way over here, this is the critical point. And the critical point is where, if you go to the bottom of this little graph, there's also a critical point right here. The critical point is the point at which you can no longer apply pressure to become a gas. To become a liquid, I'm sorry. You can no longer apply pressure to become a liquid. So once I go past it, so once I go past this point right here, past that point, no matter what pressure I have, it'll always stay a gas because it is under the conditions, it has too high of a temperature. All right, let's keep going. Point C, where's point C? It's right here. What phases are occurring? So I'm assuming point C is talking about this whole line. So what phases are occurring between a solid and a liquid? So when I'm changing between a solid and a liquid, or a liquid and a solid, that is called melting and freezing. So if I'm going from a solid to a liquid, that is called melting. Like an ice cube. If an ice cube is turning into a liquid, it is melting. Vice versa, if I had a glass of water and it turned into a solid or a block of ice, I am freezing that water. So if I'm going the opposite way, it is freezing. Okay. What phases are occurring at D? Okay, so here's my letter D down here. So it's talking about this line right here. So when I'm going from a solid to a vapor or a gas. So if I'm going from a solid to a gas, that is called sublimation. Remember we saw sublimation when I showed you dry ice. Dry ice changes from a solid to a gas. It never melts at room temperature. Under the pressure of this room. And if I'm going the opposite way, where I'm turning from a gas to a solid, that's called deposition. And let me write it here, sublimation. And deposition. And what the heck, let's just put the other ones as well. Going from a liquid to a gas, that is vaporization. And going from a gas to a liquid, that is condensation. Okay. Next part. Where would the normal boiling point, normal boiling and melting points occur? Okay. So there's that word normal again. I don't know if you remember, but when we were talking about normal, there was a dotted line that had to be on the graph. That dotted line has to be at 1 atm. 1 atm. And I'm going to put a dotted line all the way down. This right here is called my normal line. And so it says, where would the normal boiling point and melting points occur? So melting point is going from a solid to a liquid. So if I'm looking on that normal line, if I'm going to go down that normal line, I'm going to hit this point right here where the melting occurs from a solid to a liquid. This would be the normal melting point right there. Let's label it. Normal. I'm just going to put NP for melting point. And then the next one, what is the normal boiling point? Boiling is from a liquid to a gas. So here's my point right here, liquid to gas, right there. That is going to be my normal boiling point. And there we go. There goes my phase diagram. We'll talk more about this on Monday. Just wanted you to get the notes down. Let's move on. Here's called a heating curve. This is kind of the same concept, except I'm adding energy and it's turning into from a solid to a liquid to a gas. Okay? So it just depends on how much energy I'm increasing it by and what is the temperature I'm increasing it by as well. And so my first state down here at a low temperature, right here, at a low temperature and at a low energy, I'm going to have a solid. Then I'm going to heat it up, and so I'm going to add energy, and then slowly it's going to start to melt. So I'm going to put melting here. It's going to melt, and it's going to turn into a liquid. And then if I keep going, I'm going to soon start to boil it. We call that vaporization. And now we've turned it into a gas. If I'm going the opposite way, I have gases, and they're going to turn into a liquid. That is called condensation. And if I have a liquid and I want to go to a solid, that is called freezing. Okay? And so knowing that these are the three different types of states, and these are what the phase changes that they're called. So as I'm adding energy, I'm changing the state. If I'm removing energy, I'm changing the state as well. So looking at this part, whenever you have a graph like this, label what is a solid, what is a liquid, what is a gas. So right here, this is my solid, this is my liquid, this is my gas. The straight lines are where the phase changes are occurring, so melting, freezing, all those things. So the first part, where does freezing begin? I know freezing, if I'm thinking of freezing, I'm thinking, okay, if I have a glass of water, it's going to freeze into an ice cube. So I'm going from a liquid to a solid. So let me write that. I'm going from a liquid to a solid. So I'm starting at letter C, and I'm turning into a solid. So where does freezing begin? Letter C. The next one right here, where does melting begin? Okay, so if I'm thinking of melting, I have an ice cube and it's melting in my hand, turning into a liquid. So I have an ice cube, a solid, and it's turning into a liquid. So where does it begin? It begins at letter B. Oh, sorry. And so I have a solid becoming a liquid. Vaporization. Okay, if something's going to vaporize, it's going to start to boil, and so I'm going from a liquid to a gas here. So from liquid to gas. So where does it start? It starts at letter D. And the last one, condensation. Condensation is when I go from a gas to a liquid. And so where does that begin? It begins at letter E. And there we go. Okay, and that's as far as you need to go for today.